let's now take and let's stick with sine and cosine right now, and then in the next couple sessions we'll focus on those other 4 trig functions, okay? As far as graphing skills and shifting and stretching and squeezing. So what I want to focus on in these last few minutes for this segment are some applications, some real-world applications, and there's a little bit of vocabulary associated with this stuff as well. So we're going to do an application problem, and I could make my own up, but I think I'm just going to go ahead and grab something out of the book, and we can use the vocabulary, or I can introduce the vocabulary in the context of the example. The problem I'd like to do is deals with alternating current. We've all heard about that. Have you ever taken a motor, an engine, and had the motor going, and you're in there in the engine compartment playing with it in an automobile, and you accidentally touch a spark plug? You have? Okay, and you have, and you have. Anybody else? Oh, how'd you do that, Elizabeth?
I have a classic car. It's all kinds of fun.
Oh, okay. And in the old cars, the spark plugs and the wires are sticking right up there. If that motor's going, you have a generator that's creating quite a bit of power, electrical power, and that power goes through those wires into the spark plug, which fires the gases that are inside the cylinder to make the car go. You accidentally touch that spark plug or that wire, and what happens? You get a pretty good zap. It probably kicks your hand right off of there. Even more dangerous than that is the electrical current we have in our culture, which we know rises and falls in its voltage very rapidly. Anybody know how many times per second? 60 times per second it goes through a cycle. 60 cycles per second. So it should make sense to you that we're dealing with a sinusoidal model for alternating current. It's going to rise and fall, and it's dangerous if you touch yourself to that kind of current, because what happens is it interferes with the electrical pulses that cause your heart to beat. And if you've got something hitting you at 60 cycles per second, that's significantly different than the electrical pulses that come to your heart, and you can actually get electrocuted that way. So here's an application related to alternating current. We're going to write down what's called voltage, and it's a function of time. Is a function of time. And a very fundamental model in our country, other countries in Europe and other parts of the world use a different cycle, use a different alternating current cycling structure, but we use this kind of structure. So we can build a sinusoid model with 120 pi times time. The questions being asked in this particular problem out of the text, which I'm using, if you're using our textbook, it's number 96 on page 409. But here are the kind of questions being asked there. It could be in any algebra book or physics book or fundamental electrical electrical fundamentals kind of course. Is what's the amplitude and period? Amplitude, question mark, period, question mark. And then in part B, they want the graph. They want us to graph it for 2 cycles. Graph for 2 cycles. In part C, actually I think what I'm going to do, yeah, let's go ahead and do it, since you might as well learn a little bit about electronics while we're at it, is it's saying, figure out what the current is. What is the current? And that's going to be the letter I is traditionally used for current. If the resistance is 20 ohms. If the resistance is 20 ohms. Now, there's a rule that allows you to compute current if you know the voltage and the resistance. And that's a very simple rule or law. Voltage equals current times resistance. Okay, so that's the problem that's posed in the book. And I want us to go ahead and address it. We only have, 6 or 7 minutes left. So this is not going to be too hard if you understood what we did previously. The independent variable is now not an angle anymore, is it? It's now time. And this is time in seconds. Okay. So I want to set this up just like I did the previous sinusoid model. So we would have our voltage divided by our 120, and we're going to take and write the sine as time divided by what? It's just a number. It's like 3 we had previously. 1 over 120 pi. Now think about what's going on here. You've got a sinusoid model that is going to oscillate between what top value and what bottom value? 120 top minus 120 bottom. So it's going to be an oscillator between those boundaries. Okay, this is a vertical stretch just like we did previously. And over here, this is a very small number. That's smaller than 1 over 360. 1/360th. It's going to take that thing that normally finishes a cycle in 2 pi, right? And it's going to make it smaller than 1/360th is wide. Jams it together. And you're going to see in a second, or in a minute or two, that this thing goes through a cycle in 60 cycles in every second. 60 complete cycles in every second of time. So this is how you transform a trig function that you're used to thinking of this as an angle into a time-dependent function. So we have grabbed this thing and we have squeezed our basic sinusoid by a multiple of 1 over 120 pi. So what is the period? Normally it's 2 pi multiplied times that compression factor. Look what happens. You get 2 over 120. The period is 1/60th of a second. What do you think? Is that all right? Okay. So don't get nervous when you see some strange looking thing. Just look at the fundamental structure that exists, whether it's algebraic or trigonometric. Just look at the fundamental structure that exists and use the fundamental skills that you've developed.
So you multiply it by 2 pi because that's the period.
Yeah, the period of a regular sine wave, a fundamental sine wave, is 2 pi. And I'm not using degree measure anymore because I want to be in real number form. Because I want to transform things I don't want to use degree measure because I want to get into real number values. And what this does is it allows us to transition into time instead of it being degrees. Okay, so we use radian measure. We use radian measure for the fundamental period and multiply it times the compression factor. There's the period. One more comment about that before we continue answering these is the period is 1 second per 60. You can think of it as 1/60th of a second for the period, but also think of it as 1 second to complete 60 cycles. Does that make sense? It's going to finish 60 of those sine cycles in 1 second. Is that all right? If we turn this upside down, we're going to get something we call typically F, frequency. Frequency is 1 over the period. Try not to forget that, and look at what you, please wait. You're not, oh, I'm sorry, okay. And so what we end up getting is the reciprocal of this is notice that we get 60 cycles per second. That makes sense to you. You've all heard of that, cycles per second. Okay. So we got the amplitude. Let's answer the questions here. 120 volts is the amplitude. And the period is 1/60th of a second for the period. They want us to graph 2 cycles. Let me come back to the other board here. We just draw a sine wave, don't we? And they said draw 2 cycles. So we don't have to be too fancy, and we don't have to make it real compressed. We can just lay it out here nicely. And so this is time, and this thing's going as high as 120 and as low as minus 120. It finishes a cycle in 1/60th of a second. But how do we like to do our graphing? Do what with a period? Cut it into quarters. A quarter of our period is 1/4 of 1/60th or 1/240th of a second. So here's a 1/240th of a second, 2 2/40ths, 120th of a second. 3 of them is here, 4 of them is there. This will finish it in 2 periods. This is 2/60ths or 1/30th of a second. There's the sketch, 2 cycles. What's the current if the resistance is 20? Well, all you have to do is take and solve this for the current is equal to your voltage function divided by the resistance. So all we're going to do is take this original problem and divide it by 20. Reduce the 10 out. You with me on that? And then you end up getting a sine wave. The current is 6, and the units on that, the amplitude of this is going to be 6, the same sine function here. Did I make any mistakes in the arithmetic, or is that okay? I think I'm okay, right? And so the result here, the units, the word we use for current is amps. You don't need to know too much about that for this course, but certainly if you take applying this mathematics to science, you're going to need to learn some of that stuff. Okay, I think that in a nutshell covers it today. And don't forget there's a couple things, a homework quiz due by 5 today. And then there's a homework quiz for this week's material that is then due next Tuesday by 5. Quiz 2 is going to be due by towards the end of next week, and that'll show up in Math XL for you.